Now we're going to discuss an important application of the inverse function theorem called the implicit function theorem. So the statement is the following. You take three Banach spaces, which I'm going to call capital X, capital lambda, and capital Y. Lambda, you must think of it as a parameter space. Then an open set, which is contained in the product X times lambda. And u naught lambda naught a point, and a function f which is defined on O with values into y. Okay, so what assumption are we going to make in addition to these data? Suppose first that u naught lambda naught is a solution to the equation f of u naught lambda naught is equal to 0. Okay, assume in addition that f is Cp near the point, so near the point u naught lambda naught for some p bigger than 1. Assume also that its partial differential with respect to u is an isomorphism, a bijection from x to y. And the conclusion to all this is that there exists a ball in parameter space, so let's call it B, centered at lambda naught and of radius r, let's say. And there also exists a neighborhood, capital U, of the point u naught, such that if we want to solve the equation f of u and lambda is equal to 0 whenever u belongs to u and lambda belongs to b, then this is the same thing as asking that u is a curve depending on lambda. Okay, so still for u and u and lambda and b. I say a curve because I'm thinking of the parameter space as being one-dimensional, but it could be many-dimensional or even infinite-dimensional. And the last thing is that the curve or the parameterized function u of lambda is of class Cp. All right, the proof of this theorem, once you know the implicit function theorem, is rather simple. You take a new function g, which is going to define still on O, but this time with values in y times lambda, and which to a couple u lambda assigns f of u and lambda as a first coordinate, and lambda as a second coordinate. So let's check that this g satisfies the assumption of the inverse function theorem. So, well, the smoothness assumption follows easily from that on f, and we just have to compute the differential of g at the point u naught lambda naught. So let's see. First, have to differentiate this with respect to u. We get du of f computed at still the same point u naught lambda naught. Then we have to differentiate with respect to lambda. And then we have to differentiate lambda with respect to u, which is 0, and lambda with respect to itself gives you the identity in lambda. And so clearly, because of the form of the differential, this is going to be an isomorphism from x times lambda onto y times lambda. So now we know that g satisfies the assumptions of the inverse function theorem. And so this means that g is a local Cp diffeomorphism near the point that we started from, which was u naught lambda naught. And what that means in particular is that if we want to solve the equation g of u and lambda, which is equal to 0 lambda, and we do this for u in some small neighborhood of u naught, and for lambda in some small ball around lambda naught, then this is really equivalent to asking that u lambda is g inverse of 0 lambda. And what this says is exactly that u is a curve depending on lambda, or a function of lambda only, with a Cp dependence to it, as follows from the inverse function theorem.